And on to example 5, which is a real-life problem relating to the maximum load in a lift. This requires us to use sums of random variables. We have a lift certificate that states the maximum load is 800 kilograms and capacity 11 people. So our problem here is, suppose we have those 11 people. If the 11 people follow a normal distribution, so we're given that the weights of adults are normally distributed with a mean of 73 kilograms and standard deviation of 13. What's the probability that the elevator will be overloaded if it's filled to capacity? So to be overloaded, it means we're looking for the probability that the total of the weights is bigger than 800 kilograms. And in order to do that, we have to make certain assumptions. We're told that the people are normally distributed, so we can take the total load and think about that as a random variable, as long as we can consider the people as being individuals and therefore independent of each other. So the people are independent of each other, and we can use the sum of the random variables so long as we can make that assumption. It may not be reasonable. People don't always travel independently, but we'll make that assumption in order to do this problem. So to do the problem, what we're looking at here is a situation where we have the load we'll call L, and that is the total of the number of people, the total load, and we'll call P the random variable for the people, the person. So our load is here, the total weight of those 11 people, so person 1 plus person 2, person up to person number 11. And so the expected value for the load is the expected value of person 1 plus the expected value of person 2 plus the expected value of all the others up to and including person 5. And each of these are individual. It did mean 11. So up to person 11. And these are all independent random variables which take values from that person distribution. So we're just looking at 11 times the expected value of P. Now recall that expected value of P was given as 73 kilograms. So 11 times by 73, which is equal to 803 kilograms. Similarly, we can find the variance of L. And the variance of L will be the variance of person 1 plus the variance of person 2 and all of those others up to and including person 11. And recall again, this will be equal to 11 multiplied by the variance of person 1, which is, or person, we'll just say the variance of the person, 11 multiplied by 13 squared, because we were given here that 13 was the standard deviation. So 11 times 13 squared, which comes out at 1859. So to find the standard deviation for the load, we need to take the square root of the variance, the square root of 1859, and that comes out at 43.12 to 2 decimal places. So now we can look at this distribution for the load, and we can consider the fact that if each of the people is a normal random variable, then the load is also a normal random variable, and it has parameters of 803 for the mean and 43.12 to 2 decimal places for the standard deviation. And again, because we're looking at the load as the distribution here, we're needing to calculate the probability of being over full, over capacity, over the maximum load, and that means the probability that the load is bigger than 800 kilograms. So if we have our mean at 803, the probability that the load is bigger than 800 kilograms, there will be the area to the right of 800 on that graph at the bottom, the diagram, where that horizontal, the horizontal label will be for L for the load. So the probability that L is bigger than 800 we can find by using XL norm dist, and because it's an area to the right of a value, we would write 1 minus the probability that L is less than 800. That makes 1 minus norm dist from XL. We'd need 800 for the X value, 803 for the mean, 43.12 for the standard deviation, and 1 for cumulative. And so we'll go into Excel now just to show the calculation for that. So recall in Excel we need to choose the function norm dist, and for XL we need to put in X as 800, we need the mean value of 803. The standard deviation here to 2 decimal places, we had 43.12, and 1 for cumulative will give us the area up to that point. And we'll use there 0.4723 to 4 decimal places. So here we're writing equals 1 minus 0.4723, and that comes out to be 0.5277. 0.5277, which is the same as 52.77, nearly 53% likely. So this is a very large probability, and exactly what we wouldn't want to be happening. 53% chance of having the lift overloaded if it was filled with 11 people.